Thank you, ladies and gentlemen, for showing up for this seminar this afternoon. I'm delighted to have this opportunity to visit the University of Waterloo and discuss my work. And I'd like to thank Pavla and Arthur for the invitation to come. And I have to say that I don't believe I've ever stood before a larger screen than this one. So let me tell you that the work I'll discuss today was done by Dr. Yixin Liu and Dr. Fudong Wang in my group, two recent graduates. We collaborate with my physics colleague, Patrick Gibbons, who helps us with TEM and diffraction. And the work was also done by Ginny Wayman and John Glennon, who are students with my colleague, Rich Loomis. And they have contributed the optical microscopy and confocal microscopy and spectroscopy that you'll see in the talk today. And the funding is from the National Science Foundation and the Center for Materials Innovation at Washington University. Okay, so over the last decade or possibly decade and a half, the nanowire research has developed into a really large field. And that's in part due to the interesting physical phenomena that nanowires and quantum wires exhibit, and also because of perceived applications that may emerge for these kinds of materials. And so my group has been very interested in studying two-dimensional quantum confinement in these wires. They're very long. They're not quantum confined in the length dimension, but they are confined in the two radial dimensions. And two-dimensional quantum confinement is different than three-dimensional and one-dimensional quantum confinement. There's also anticipated, nanowires also have the potential to transport energy and charge over long distances. And that may provide support other applications in, for example, solar energy conversion and other things. So the fundamental question that I'd like to address and that my group has been working on very hard for the last couple of years is the question of, do semiconductor nanowires transport energy and charge efficiently? The nanowires we now have, how well do they do this? Can they do it? And if they cannot, what factors limit that transport? And how can the transport efficiency be optimized? And so that's what I'd like to discuss with you this afternoon. I'm going to suggest a potential application to sort of motivate the rest of the discussion today. You may well know that there's several groups working on quantum rod solar cells of this kind of architecture, where quantum rods are dispersed at high densities in a whole transport polymer. And the idea behind this kind of a device is that the semiconductor quantum rods are the chromophores, and they capture photons and generate electron-hole pairs. Those electron-hole pairs are then separated, and the hole is sent to one electrode through the whole transport polymer, and the electron hops its way to the other electrode. And that is an efficiency issue, because every time a charge crosses an interface, there's a good chance that it will become trapped and never collected at the electrode. And additionally, these kinds of structures can have dead ends. And so there's been quite a bit of discussion over the last few years in the field that it might be possible to replace these rods that have rather short lengths with wires that are much longer and perhaps can span a large fraction of the inter-electrode space in such devices. And then you can see that a photo-generated electron-hole pair can allow the hole to jump into the whole transport polymer, and the electron can potentially be transported along the length of the wire to the other electrode without ever crossing an interface. So the question is, can that really work? And the problem, although there's lots of potential advantages for quantum wire or nanowire solar cells, there's some really serious challenges. Quantum wires, like all nanocrystals, have large surface or interfacial areas, and that's where bad things happen, generally. And so recombination at surface or interfacial traps and other trap sites have to be minimized. So the idea is you need to have a wire that's sufficiently free of defects that a charge or an exciton can actually transport along its axial dimension without becoming trapped. We'll be addressing that specifically today. So here's a brief outline. I'd like to first review with you the synthesis that we have developed for colloidal semiconductor quantum wires and speak briefly about some basic optical and spectroscopic properties of quantum wires. I'll discuss passivation of quantum wires to improve the optical properties, and then I'll report on the surprisingly good properties of quantum belts. And finally, I'll conclude with a brief discussion of our recent efforts in the SLS growth of quantum wire films. So some years ago, we discovered this so-called solution liquid solid mechanism for growing nanowires. And over the years, we've developed it into a nearly general synthetic method. This is done in solution or solution dispersion, much in the way that colloidal quantum dots are grown. In fact, we use very much the same precursors. We use the same kinds of solvents, the same kinds of temperature ranges. We use the same kinds of surface passivating agents. But the key difference in this synthesis is that we purposely added dispersion of nanometer-sized metallic particles that catalyze the wire growth. And so here's how it works. The precursors to the semiconductor phase decompose in solution and at the interface between the solution and the liquid catalyst droplet, because under the reaction conditions, the catalyst droplet is actually molten. It's a liquid. And that deposits the elements of the semiconductor phase into solution in the metallic droplet. The metallic droplet becomes supersaturated. And to relieve the supersaturation, it has to precipitate the semiconductor phase. And it does so by forming a liquid-solid interface and precipitates the semiconductor as a crystal. But that's the only active crystal growth interface. So layer after layer after layer of semiconductor crystal is deposited here, and as that happens, the semiconductor wire then is ejected from the droplet. So that's the part of the wire that grew first, that's the part that grew last, and as long as we continue to feed precursors to the droplet, the wire will continue to grow. And because that's the only crystal growth interface, the wire develops a naturally approximately isotropic cross-section. And we can now grow fairly narrowly dispersed quantum wires with diameters in the range of 3 to 20 nanometers. In fact, we can grow outside that range on the high end, but there's not much excitement in terms of quantum confinement at these larger diameters. And our lengths are tens to hundreds of micrometers, depending on the cases. And we use, as I mentioned, the traditional quantum dot surfactants. And we can now grow a very wide range of materials in the 2,6 family, and in the 3,5 family, and in the 4,6 family. So because we can control the size of the catalyst droplets, we can control the diameters of the wire. In fact, our rule of thumb is that the diameter of the wire will be approximately 1/2 the diameter of the catalyst particle. So since we can now synthesize monodispersed catalyst particles of a range of sizes, we can grow quantum wires with a range of diameters. We typically use bismuth. This is the most generally applicable catalyst material, although there are other materials that will work. So here's some examples of CAD Telluride quantum wires having different diameters, which we've purposely grown over that diameter range. And you can see that they are straight and they are, let's see, roughly all the same diameter. In other words, your eye tells you at least that the diameter distributions are reasonably narrow, and you can see that here are the distributions expressed as a percentage of the mean diameter. This is one standard deviation in the diameter distribution expressed as a percentage. They're also essentially or almost single crystalline character. And here I show on this slide what's the main kind of defect behavior or defect characteristics found in the wire. These are high resolution images, and if you have a sharp eye, which my postdoc does, you can actually look at this and assign regions to their various crystal structures. So CAD selenide we would normally expect to exhibit the Wurtzite structure, but what we can see is that there are regions in this wire that are Wurtzite, and they're interrupted by domains that are zinc blend, and then Wurtzite and zinc blend, and so on. And in these CAD selenide wires, the mean segment length for a Wurtzite segment is about 6.3 nanometers. The zinc blend mean segment length is about 1.8, which means that the volume ratio in the wires is about 3.7 to 1 for Wurtzite to zinc blend. I'd like to eliminate this sort of zinc blend Wurtzite alternation if I could figure out how to do it, because I think it probably limits the optical properties. I think that at each of these sorts of interfaces between zinc blend and Wurtzite regions, there are probably surface defects introduced. I don't have any proof for that. That's a speculation. But this, other than this sort of structural alternation, the wires are single crystal in character. Here's some TEM images of CAD Telluride quantum wires. You can see these look rather nice and uniform. You can also see that there's a strong tendency for these wires to align in parallel bundles when they're deposited from solution. So there's strong van der Waals and dipole-dipole attractions between the wires. So you can make a nice dispersion of wires in toluene, for example. It'll look just like a colored solution or a colored suspension. If you put that vial on your desk and go off to lunch and come back, the wires will already have begun to bundle because of these favorable interactions. And when the bundles get large enough, they start to precipitate. So when you come back from lunch, you'll see a little clear solution at the top of your vial. If you wait long enough, they'll all settle out into these sorts of bundles. But you can merely swirl the vial and they'll go right back up into suspension again. And that's because they have long alkyl chain surfactants attached to the surface, which give them dispersibility. You can also see the catalyst particles attached to the ends of many of these wires, and these are the particles from which the wires grew. Okay, and here's some examples from 4/6 wires. So we can actually grow quite a wide range of materials. Okay, a little bit about the spectroscopy of quantum wires. So I mentioned to you that if the diameters are small enough, these wires will exhibit two-dimensional quantum confinement effects. And you can see that here in these spectra in two ways. The first is this lowest energy transition is the one that we use to measure the effective band gap. As the diameter gets smaller, you expect the effective band gap to get larger. And that, in fact, you can see, because here's a 10.5 nanometer wire, and you can see this has the lowest energy transition, and the effective band gap increases and increases as the diameter decreases. You can also see a number of additional features in these spectra. They're not real clearly resolved, but those are all due to the fact that the electron and hole wave functions in a cylindrical quantum wire behave as that they're trapped in a cylindrical box. And that's pseudo-discrete energy levels, particle-in-a-box levels in the wires. And all these additional features can be assigned to various transitions between these particle-in-a-box states. And these only exist because of quantum confinement. Okay. Now, wires also exhibit photoluminescence, and in fact they exhibit band edge photoluminescence, which is a good thing. Here's the band edge. This is where the first excitonic transition occurs. We can excite higher lying excitons, but a higher lying exciton will always relax to the band edge before recombining radiatively. So all the photons come out here at the band edge. And that, of course, is diameter dependent, just as the first excitonic absorption feature is diameter dependent. So I show here a photoluminescence efficiency in the range of 1 to 2% for CAD solenoid quantum wires, and we actually had to work very hard to get that. And so let me just be clear what a photoluminescence efficiency is. We're generating these excitons or electron-hole pairs with light. So photon absorbed generates an electron-hole pair. If that electron-hole pair recombines radiatively, the photon comes back out. That's photoluminescence, the radiative recombination. If every photo-generated electron-hole pair recombined and re-emitted the photon, our efficiency would be 1 or 100%. The fact that this is only 1 to 2% says when we generate 100 excitons, only 1 to 2% of them are recombining radiatively. So is that good or is that not good? Well, we'll be discussing that at some length. It turns out that those sorts of photoluminescence efficiencies are actually very good in comparison to what's currently in the literature. But obviously, for applications or to enable fundamental physical studies, that's pretty low. Let me just make one point explicitly clear here. I seem to be very committed to photoluminescence efficiencies, which is actually the radiative recombination of electron-hole pairs, whereas certain applications, like solar energy conversion, focuses not on the recombination, but on the separation of electron-hole pairs. But one thing is certain. that in all of the potential quantum wire applications will require transport of charges, charge carriers, or excitons along the long axis of the wire. And in order for that to happen, trap sites must be minimized. That allows efficient charge transport. So we're going to use photoluminescence efficiencies as indicators of efficient surface passivation. So first we'd like to learn how to adequately passivate the surfaces of the wires to eliminate traps, and later on we would engineer in ways to purposely separate charge carriers for solar energy conversion applications. So there's a few things that can be used as indicators of efficient surface passivation. PL efficiencies, as I'll discuss in a moment, exciton diffusion lengths, which we're going to actually study here this afternoon, and carrier mobilities, which we've done a little bit of work with, but I will not discuss today. Okay, so let me put this PL efficiency issue in sort of a historical context. And I'd like to first talk about quantum dots. And I show you here a quantum dot that has an exciton in it. An electron hole pair has been generated. And if that electron hole pair remains delocalized in the core of the dot, the wave functions of the electron and hole will overlap significantly, and there will be a high probability of radiative recombination. So in this scenario, the photoluminescence efficiency will be high. But if there are trap sites on the surface of the dot, then the electron and hole can become trapped on the surface, localized, where their wave functions no longer overlap. And here the probability of radiative recombination is low. And so PL efficiency is a measure of how well the surface is passivated. A high PL efficiency tells you that trap sites at the surface of the nanostructure have been minimized. And 20 years ago, early in the quantum dot field, the band edge PL efficiencies were essentially zero. All the photoluminescence was red-shifted trap emission, which meant that the surfaces were highly defective. But the passivation schemes have developed over the last 10 years or so, such that now the PL efficiencies in quantum dots are routinely 60% and above, and in rare cases in some cases approach near unity. So the problem has really been solved for quantum dots, and quantum dots are now very well passivated. What's about the case for quantum rods, which are just elongated dots? There, the optimized efficiencies, PL efficiencies, are in the order of 20 to 30%, which is still really excellent, but it's about half of that for dots. So there's various arguments to describe why these are smaller than these, but my opinion is simply that a rod has a larger surface area than a dot. And therefore, there's a higher probability that there will be a trap site, or more than one trap site, that the carriers can encounter. And because of that, those efficiencies will go down. Now, here are the efficiencies published. They're currently in the literature for quantum wires. These are devastatingly low, 0.02 to 0.2%. And obviously, the case for wires is severe because now electron hole pairs can make excursions along the long axis of the wire looking for trap site defects where they can become trapped. So obviously then, in equally well passivated dots, rods, and wires, the efficiencies will always be lowest in the wires. So the question is this problem so severe that it's practically hopeless to think about wires in which carriers and excitons can be efficiently transported? It's a big problem, and maybe it's unsolvable. Well, we did, Rich Loomis's group and mine did an experiment a few years ago. Sorry. A few years ago. Oh, I see the problem. I came unsnapped. There we go. Forgive me for that interruption. And what I'm showing you here is a epifluorescence image of a single CAD Telluride quantum wire. And you can see that it's blinking. And that's really not surprising because individual molecules blink and quantum dots blink. And so many things blink. That is, they show, if you continuously irradiate them, they will show fluorescence intensity fluctuations, even as much as on and off. So that's not particularly surprising. But what's surprising is the pattern of this blinking behavior in this wire. Because as you may have noticed, the intensity fluctuations were completely synchronized all the way along the entire length of the wire. And if you have a wire with a highly defective surface, you do not expect to see that kind of behavior, because no exciton that's generated in one spot could survive long enough to be transported to some other area of the wire. That is to say, the blinking phenomenon should be localized. And if you see fluctuations, they should be in uncoordinated, localized twinkling manner, like a string of uncoordinated Christmas lights. And in fact, 98% of the wires in our specimens give exactly that kind of twinkling behavior. It's only 2% or so, 1 to 2% of our specimen that shows this kind of blinking behavior. Synchronized, whole wire blinking. And moreover, when these wires, rare wires, are in their bright state, their individual quantum efficiencies, photoluminescence efficiencies, are 20%. That's competitive with rods. So what it says is that so the way we interpret this is that the whole wire blinking phenomenon reveals that excitons are able to be transported or delocalized along the entire length of the wire. Otherwise, we could not have this kind of synchronized blinking behavior. So what that tells us is that there's a small proportion of our quantum wires that do have low trap site densities and do effectively transport excitons. And the question is, how can we make the other 98% behave like this? Well, we can't quite answer that question yet, but let me show you in another system. This is CAD Telluride now, that with various surface passivation schemes, we can actually dramatically improve the bulk photoluminescence efficiencies of our specimens. So here are these are the photoluminescence spectra of CAD Telluride quantum wires, and this black trace is the spectrum, PL spectrum, as synthesized when we get the CAD as the CAD Telluride wires are first obtained from the synthesis. You can see there's no PL. And then if we first passivate sequentially with ethane thiol, we start to see a little photoluminescence. If we photoanneal, that is, just expose the wires to strong light, a feature starts to emerge. And then if we then treat later with trioctylphosphine, we can actually optimize these bulk or ensemble quantum yields, quantum efficiencies to 5 to 8%, which is getting to be respectable. And if we look at individual wires, we see that the well-behaved ones are bright, uniformly bright, and they have uniform spectra all along the length of the wire. So that's this observed efficiencies in the range of 5 to 8% is an improvement of about 2 orders of magnitude over what's been published, and they're almost becoming respectable. Okay, now let me talk to you about quantum belts. And we never intended to work with quantum belts. We wanted small diameter wires, and there was a synthesis in the literature describing how to get small diameter wires. It turns out that our SLS method, the catalyzed method, has a limitation. We can really only make 4 or 5 nanometer wires at the smallest. It's very hard for us using that method to get smaller, but a lot of interesting things happen with smaller diameter wires, so I desperately wanted to have some. There was a synthesis in the literature that's a non-catalyzed synthesis that was described as a, let's see, what was it called? An oriented attachment mechanism is the way it was described. And I don't care how they form. At that point, I wanted the wires. And so I asked my student to go and reproduce the synthesis, which he did. In fact, he reproduced it several times, and it never gave wires. Instead, it always gives belts that have a width, a significant width, a fairly long length, and a very thin thickness. And so what you see here is how the belts are first obtained from the synthesis. This is actually a bundle or a stack where the belts are stacked up face to face to face to face to face to face. And if you look at that sort of a bundle at higher resolution, you can actually measure the thicknesses of the belts. So here's one belt, here's another belt, here's another belt. These are all stacked one upon the other, upon the other, upon the other. And the thicknesses of these belts is 1.8 nanometers. We can then unbundle the belts by sonicating these bundles in the presence of a long chain amine, and the bundles come apart. And now we can see the broad top and bottom faces of the belts. And we can see that they're on the order of 7 to 15 nanometers wide, and they're on the order of 1 micrometer long, which is much shorter than the wires that we can make by the SLS method, but that's reasonably long in comparison to the exciton dimension. So it turns out that we were very surprised to find that the photoluminescence efficiencies in these belts can be as high as 40%. 40%. And who would expect that? Because after all, a belt has a larger surface area than a pseudo-cylindrical wire. If anything, the efficiencies should have been lower. We never expected this. So obviously with that, it occurred to me that belts can be wires too, right? That could potentially transport energy and charge over the long dimension. And these efficiencies are so high, it indicates that there's something good about these belts. Additionally, in the last, when I showed you the quantum wire blinking, I told you that it's only 2% of the wires exhibit that blinking, a whole wire blinking behavior. But all of the belts do. So all of the belts, by that criterion, would seem to have exciton delocalization along the entire length of the belts. These have a Wurtzite crystal structure, by the way, it so happens, and we don't find any zinc blende domains in these belts. Here are some optical microscopy images of these belts. Here's a bunch of belts just showing you that all of them are bright, and you might say, wow, they don't look very much like belts, they look more like cough drops. But remember, the resolution of this optical experiment is rather low, and so that belt looks like it's roughly 550 nanometers wide, but it's only 7 to 15 nanometers wide, and it's about roughly a micrometer or so long. And we can measure the photoluminescence spectra from a bunch of individual belts, and they all line up very closely to the same energy value, telling us that the thicknesses of the belts are remarkably uniform. Remarkably uniform, more uniform than the diameters of the wires that we can make. So let me also clarify one more thing. These are fairly wide, 7 to 15 nanometers wide. They're quite long, a micrometer long, but they're thin. So these belts exhibit one-dimensional confinement. They're only confined in the thickness dimension. And that will come back to have some importance in a few moments. Okay, well, we did an interesting experiment. Rich's group, Ginny and Rich, did an interesting experiment to establish that the excitons are in fact delocalized along the entire lengths of the belt. And so this is what they did. They irradiated a belt with a small spot size right in the middle of the belt. And then they measured the intensity profile along the length of the belt. And this is the emission intensity profile along the length of the belt. And so the maximum emission intensity is right in the middle. Well, you might say that's not so surprising because, in fact, that's right where the belt's being irradiated. However, Ginny then moved the spot off the end of the belt so it was just overlapping with one end. And that's this experiment here. And then she again plotted the intensity profile over the length of the belt. And again, the maximum intensity is right in the middle of the belt. And then we did a simulation as to what should the intensity profile be if there's an equal probability of emission everywhere along the length of the belt. And that gave us this, which is to say that no matter where the exciton is generated, it has an equal probability of recombining and re-emitting at any point along the length of the belt. That is to say, excitons are effectively delocalized along the entire axial dimension of the belts. Okay, we thought that there must be something interesting about the population of defect sites on these belts that might justify why their optical properties were so much better than those of the pseudo-cylindrical wires. And so to try to identify this sort of population of defects on the belts, we did a decoration experiment. And decoration experiments, the strategy behind a decoration experiment is as follows. If we're all looking off into the distance at some telephone wires, if the poles are far enough away, we can see the poles, but we can't see the wires. until a flock of crows comes along, and the crows sit down on the wires and decorate the wires. And now we can sort of see the wires because we can see the crows. We know where the wires are because the crows have decorated the wires. And that's the concept behind a decoration strategy here. And the first time that a decoration strategy like this was used in science and engineering, to my knowledge, was in the 1930s, when the goal was to identify the surface cracks, microscopic surface cracks on glass. And this is at a time when there was no electron microscopy, and these cracks were so small you can't see them with an optical microscope. And so you take a piece of glass and you expose it to mercury vapor. And the mercury vapor cools and condenses on the surface of the glass, but it nucleates particles preferentially on the defect sites on the glass. And so if this experiment is done carefully, one can actually decorate the surface cracks, count their density, and relate that density to the strength of the glass. This kind of strategy was later used to identify the emergence of dislocations from crystals in the 1950s. I think, I may not be right, but I think this is the first time the strategy's been applied to nanostructures. And so we carefully deposited gold nanoparticles on the belts. And to our surprise, we found that they are deposited almost exclusively along the thin belt edges and not on the broad top and bottom surfaces, which is to imply that most of the defects are along the thin edges of the belts rather than on the top and bottom surfaces. And that gives one possible explanation for the better optical properties of the belts, because these apparently defective thin belt edges make up only 14% of the total surface area, whereas they would make up on the order of 50% of the surface area on a cylindrical wire. I should have said that one has to make the assumption that the trap site defects are in proportion to the defect sites that can be decorated by these gold particles. Well, we identified the crystallographic facets on the edges of these belts, and they're different, and they're in a different family of faces than the top and bottom surfaces. So it could be just that the crystallographic difference, that for some reason that these crystallographic faces, which I've labeled in blue, are naturally more highly defective than the ones labeled in red. And so that's part of the explanation for this, for the wire. If we model the wire as a dodecahedral prism, then it has to be surrounded by alternating blue and red faces, and that would give you an equal surface area of defective and non-defective faces. I mean, that would be one interpretation. So it could just be that this has a higher population of defective faces. Well, there's other possibilities that I'm going to explore momentarily, because in fact, although these are crystallographically different, the differences are very subtle. Both the top and bottom faces and the side faces are nonpolar. They have equal numbers of cadmium and selenium atoms. The structures are subtly different. They're not markedly different. So it's hard to really push that crystallographic argument very far. It seemed to us there must be some other reason that these top and bottom faces are particularly well passivated. And so in order to explore that, I thought that it might be important for us to try to figure out how, in fact, these belt-like structures had grown. In fact, forming plate-like or belt-like nanostructures is very unusual, and it's only been known for the last 3 or 4 years, and it's not the kind of morphology that one would normally expect to occur from a solution-based synthesis. So we conducted a series of experiments to identify the pathway by which these belts grow. So let me show you that the synthesis involves dissolving a cadmium precursor in N-octylamine. N-octylamine is the solvent for this process. And we noticed that when we combined N-octylamine and cadmium acetate, we got a sort of pseudo-gel-like, pseudo-solid-like product. I mean, it's actually a precursor, but material. Let's say a pseudo-solid material. And my student, Yi-Shin, was able to get some of that into the powder diffractometer and take a diffraction pattern. And it exhibits a series of low-angle reflections that are normally associated with a lamellar structure. In fact, what has happened is the precursor has formed a lamellar-like structure in which there are layers of cadmium acetate that are separated by amine bilayers, where the amine head groups are bound to the cadmium acetate layers. And in fact, we can reproduce exactly this phenomenon in a cadmium compound that's very well known to have a layered structure, cadmium iodide, which is what I show you here. So in fact, the first thing that we form is a template structure in which we have lamellar galleries of cadmium acetate precursor separated by amine bilayers. We next add the selenium reagent, and we followed spectroscopically what happens. And what we notice is that we find a series of features in the optical absorption spectrum that have been previously assigned to CAD selenide nanoclusters, discrete nanoclusters. We first see features that are assignable to the CAD selenide 3334 and then CAD selenide 19. And over time, this spectrum evolves to the one that has been assigned to CAD selenide 13. And the theoretical structure of CAD selenide 13 is shown here in that inset. So you can see it's a very small molecular cluster. And you'll also notice that there's a very large scattering tail on this spectrum. And that's because these CAD selenide 13 nanoclusters are actually entrained within this lamellar structure. And I'll show you that with microscopy in a moment. And so these CAD selenide 13 clusters are not free to diffuse about in solution. They're trapped within the template. In fact, they're trapped within these layers between the amine bilayers. Now, if we then heat these discrete nanoclusters, they undergo a recrystallization process to give belts. And this is what you see. You see 3 features in the absorption spectrum and 1 in the emission spectrum. These 3 features are assignable to basically quantum well or one-dimensional quantum confined structures. And again, there's a long scattering tail because these CAD selenide belts are still trapped within the template structure. Now, when we unbundle them, we get this spectrum, and you can see the scattering tail is gone because we've now taken the bundles apart. And here you see the assignments, the quantum well absorption features are assigned here. Okay, so now let me show you that microscopically. So here are the assemblies of the CAD selenide 13 nanoclusters. And if you look at them, you can see that they have lamellar structures. These wispy bundles actually consist of layers, just as I suggested on the previous slide. And in fact, we still get low-angle diffraction. So these have CAD selenide 13 clusters entrained within the templates, which still have a lamellar structure. And we can sonicate these bundles in a long-chain oleolamine solvent mixture. And the bundles start to come apart. Individual layers start to unpeel from these bundles. And here are the images of those individual layers. And if you look closely, you'll see that they have a striped domain structure. We argue that the CAD selenide 13 nanoclusters are in the dark regions of the domains, and that in fact it's additional amine bilayers that are separating these striped domains from one another. And significantly, the width of these striped domains is 7 to 15 nanometers, which ultimately turns out to be the width of the belts. And for the material that remains bundled, you can see that the lamellar structure really sharpens up and has a much longer range periodicity. Okay, now after we heat these structures, we get these wispy bundles, which turn out to be stacks, vertical stacks of quantum belts. And they can be unbundled, as I showed you there, to give individual quantum belts. So let me put all of this, and finally, as I said before, the width of these quantum belts is about 7 to 15 nanometers, which was the same dimension as the striped domains on the previous slide. So this puts it all together, that the precursor in octylamine forms a lamellar template. And the lamellar template ultimately guides the dimensions and the morphology of the CAD selenide nanostructures that grow. And so initially, we grow double lamellar structures containing CAD selenide 13 nanoclusters, which are the little orange dots in this slide. So if we see this from the top, we see these vertical stripe domains. From the end, they would be stacked up in bundles like this. If we unbundle these structures at this point, they unbundle in a direction normal to the z direction to give us these individual sheets. If we anneal them, the CAD Telluride 13 nanoclusters recrystallize to form belts that have geometries that are determined by these domain sizes, and they fall apart in a direction normal to the y direction. And finally, we can completely unbundle them to individual nanostructures in that way. So the length, the width, and the thickness of these quantum belts is determined by the dimensions within this mesophase lamellar template. I wish we knew how to control the lengths or the widths of these sorts of structures, the widths and the thicknesses. We don't know how to do that yet, but that's clearly what's defining these quantum belt-like morphologies. And furthermore, I imagine, or I propose, that the excellent passivation of these top and bottom surfaces is due to the formation of self-assembled amine monolayers on the top and bottom surfaces of these belts within the template structure. Okay, let me finish with just a few results on growth of nanowire films. So if you want to, for example, make solar cells, it might be convenient to be able to grow the wires as arrays, vertically oriented arrays, right from some appropriate substrate. And when we do this, we'd like to be able to control the nanowire diameter and the spacing and density of the nanowires on the substrate. And there's some efforts to, certainly you can look in the literature and find some success in growing these sorts of arrays for zinc oxide nanowires, for example. So can we do this by the SLS method? Well, there's a few reports in the literature in which this has been done or attempted. And those attempts start with a substrate, and a bismuth film is then deposited on the substrate. And then this is the film is broken up by thermal heating to give a series of catalyst particles. But actually, this cannot be done. There's no way to control particle size with this sort of a strategy. So when you break up the film thermally, you get some small size particles and some larger ones, and you can't control the spacing. And as a result, the nanowires that are grown have a wide variety of diameters, and most of them are large, and the densities are rather low. As you can see here, these were grown by that strategy, and they just sort of fall over and lay on the substrate. And so we thought that if we instead of using thermal breakup, if we first make bismuth nanoparticles, deposit them on the substrate, we know what size they are, that we should be able to control the diameter and the spacing, the growth density of these sorts of wires, and ideally we'd like to get to here. So let's see what we can do. Well, the first thing we do is we drop cast the bismuth nanoparticles on the substrate. These are rather larger ones because they made a nice SEM image that you can see. And it's important that we, after depositing them, that we actually anneal these at a sort of an intermediate temperature. What temperature do we anneal these at? Well, in this case, about 300, because that affixes the catalyst particles to the substrate. If we don't do that, and we try to do a catalyzed growth reaction, the bismuth particles just float off the substrate, and we get just our normal colloidal nanowires. But this actually attaches them to the growth substrate, and then we take the growth substrate and we put it on a wire and lower it down into our reaction mixture, bring it to temperature, insert the other precursors, and we wait only a short period of time. It turns out that we can get significant wire growth in about 5 seconds using this method. And by the time we pull the films out, they look like this. Looks like a spaghetti mat of nanowires. Obviously, they don't look nicely vertically oriented. It could be, remember that these wires are dispersible in solvents, so it could be that in the solvent they stand up like this, but the capillary forces, when we just pull them out of the solvent, might cause them to collapse onto the substrate. So this may not be the end of the story. Obviously, I wish I were showing you nicely vertically oriented films, but nonetheless, we can control the diameters of these wires. So here are wires that are 16 nanometers in diameter. And what does that say? 12 and 7 and 5, because we can control the size of the catalyst particle. And I'll show you in a moment that these, in fact, exhibit quantum confinement effects. Initially, the initial growth is not flat down on the substrate as these appear to be. They initially start growing upwards from the substrate, but eventually they get long enough that apparently they lie down. And if we analyze the pointing angles of these wires on our silicon, I guess this was probably 100, they're randomly oriented, indicating that these wires are not having an epitaxial relationship with the substrate. And that's probably because there's quite a large lattice mismatch here. Okay, here are some emission spectra that were collected from these films. And these are from this is the emission energy for bulk CAD Telluride. And this is the emission feature for 12 nanometer diameter wires, 7, which is blue shifted, and 5, which is even more blue shifted. And these peak positions are right where they should be for wires of the diameters that we grew in colloidal dispersion. So I propose, or I submit to you, that these are the first SLS-derived films of true quantum wires. They are exhibiting the quantum confinement effect, and that's not been previously demonstrated. So now, how about density control? Well, if we put the bismuth particles on the substrate at a low density, we get this. If we put them on at a somewhat higher density, we get this. These bright spots are actually bismuth particles that are on the ends of the wires. At a higher density, we start to now see some wire bundling, which becomes extreme at even higher densities. So we have some control over the wire density on the substrates. We can grow on a range of different substrates. This is silicon 100, ITO-coated glass, polyimide. And we can grow a range of different materials, indium phosphide, indium arsenide, lead selenide, for example. So these are just some initial, fairly preliminary results of our efforts on quantum wire film growth. Okay, so let me summarize. The efficiencies and exciton diffusion lengths and carrier mobilities are all enhanced by effective surface passivation. Actually, I didn't prove this today, but we have published some work on this. Individual quantum wires can exhibit high PL efficiencies and show whole wire exciton delocalization. Our ensemble of properties are improving. So, for example, with the CAD Telluride quantum wires, we're now up to about 5 to 8%. Quantum belts seem to have excellent properties. We're making some progress on SLS quantum wire film growth. And what I'll leave you with is the factors that are currently limiting efficient exciton or carrier transport: insufficiently effective surface passivation, and I suspect, although I don't have proof, the core defects such as these zinc blende wurtzite phase alternations that I wish I could remove. And with that, I'll thank you for your attention, and I'm happy to answer any questions.